The term, quantum revolution, is more than a phrase. It represents one of the most dramatic transformations in human thought, a shift as significant as the recognition that the Earth orbits the Sun, or the discovery of the theory of evolution. It is the story of how human beings came to realize that the universe, when examined at its smallest scales, behaves in ways that defy common sense and overturn the rules that had guided science for centuries. The meaning of the quantum revolution in physics lies not only in the technical breakthroughs it provided, but also in how it reshaped our understanding of reality itself. To grasp the depth of this revolution, one must first imagine the world before it began. For centuries, physics had been dominated by the ideas of Isaac Newton and classical mechanics. Newton's laws of motion, together with the law of universal gravitation, painted a picture of a universe that was precise, predictable, and machine-like. According to this view, if one knew the position and velocity of every particle in the universe at a given moment, then in principle one could calculate its entire future. This was a clockwork universe, running smoothly according to deterministic rules. It was elegant, logical, and comforting. For more than 200 years, it seemed to explain everything from the fall of an apple to the orbits of planets. But as the 19th century drew to a close, cracks began to appear in this beautiful edifice. Experiments started to reveal phenomena that classical physics could not explain. The interaction of light with matter, the mysterious behavior of radiation emitted by hot objects, and the puzzling spectra produced when gases were energized all seemed to hint that the classical view was incomplete. These mysteries were not trivial details. They were fundamental puzzles that resisted explanation by Newton's mechanics or Maxwell's equations of electromagnetism. Scientists were forced to admit that something profound was missing in their picture of the universe. The word quantum entered the stage at this moment of crisis. In 1900, the German physicist Max Planck, while trying to solve the problem of blackbody radiation, introduced the idea that energy is not continuous but comes in tiny packets, or quanta. Planck himself treated this as a mathematical trick, a temporary fix, rather than a deep truth about nature. Yet his small step opened the door to an entirely new way of thinking. What began as an act of desperation would soon ignite a revolution. The meaning of the quantum revolution lies in the radical departure from continuity to discreteness, from determinism to probability, and from predictability to uncertainty. This was not merely an adjustment to existing laws, it was a wholesale rewriting of the foundations of physics. The universe was no longer a clock, but something stranger, more elusive, and far more mysterious. In the early years of the 20th century, discoveries came in rapid succession. Albert Einstein in 1905 explained the photoelectric effect by proposing that light itself consists of quanta, later called photons. This bold claim suggested that light, which had long been understood as a wave, also behaved as a particle. The wave-particle duality of light shattered the neat categories of classical physics. Soon after, experiments revealed that matter too could exhibit wave-like properties. Louis de Broglie, in 1924, suggested that electrons and other particles could behave as waves, a claim confirmed by experiments in electron diffraction. Suddenly, the clear boundary between matter and radiation dissolved. The revolution deepened with Niels Bohr's atomic model in 1913. Building on Rutherford's nuclear model of the atom, Bohr introduced the concept of quantized orbits for electrons. Instead of spiraling into the nucleus as classical physics predicted, electrons were confined to certain energy levels, jumping between them by absorbing or emitting photons. This explained the discrete lines in atomic spectra and gave the first glimpse of a new quantum order underlying the apparent chaos. Bohr's work, though incomplete, was a milestone in revealing that the quantum world was governed by rules unlike any known before. The quantum revolution reached its peak with the development of quantum mechanics in the 1920s. Werner Heisenberg formulated matrix mechanics, while Erwin Schrödinger introduced wave mechanics. Paul Dirac unified these approaches and laid the groundwork for quantum field theory. At the heart of these theories was the idea that physical systems are described not by definite positions and velocities, but by wave functions, mathematical entities that encode probabilities. One could no longer predict the exact outcome of an experiment, only the likelihood of various possibilities. This shift from certainty to probability was the most shocking aspect of the quantum revolution. Classical physics had promised a universe of determinism where the future was fixed by the present. Quantum physics revealed a universe of indeterminacy, where chance and uncertainty are built into the fabric of reality. Heisenberg's uncertainty principle, formulated in 1927, stated that one cannot simultaneously know both the position and momentum of a particle with arbitrary precision. This was not a limitation of measurement, but a fundamental property of nature itself. The meaning of the quantum revolution, therefore, is that the very structure of reality defies classical logic. Particles can exist in superpositions, being in multiple states at once until observed. Entangled particles can influence each other instantaneously across vast distances, challenging notions of locality and separability. The act of measurement itself becomes an active participant in shaping reality. These ideas were so counterintuitive that even great minds like Einstein struggled to accept them. Einstein famously remarked that, "God does not play dice with the universe," expressing his discomfort with the probabilistic nature of quantum mechanics. Bohr, in contrast, defended the theory with equal passion, insisting that physics must describe not how nature is, but what can be observed and measured. The revolution was not confined to abstract philosophy. The practical consequences of quantum theory have transformed the world. The invention of the transistor, the laser, and the development of modern electronics all stem from quantum principles. Today's digital world, from computers to smartphones, is a direct offspring of the quantum revolution. Even more astonishing, new fields like quantum computing and quantum cryptography are poised to reshape technology in the coming century. Yet the true meaning of the quantum revolution goes beyond technology. It represents a profound shift in the human understanding of existence. It teaches us that reality is not what it seems, that the solid objects of daily life are made of particles that obey rules beyond ordinary experience, and that certainty is an illusion. It forces us to confront the limits of human knowledge, and to accept that mystery is woven into the fabric of the cosmos. In a broader cultural sense, the quantum revolution symbolizes the courage to let go of old certainties and embrace a world of paradox. It is a story of human creativity, imagination, and the willingness to question even the most cherished assumptions. The transition from classical to quantum physics is not just a chapter in science, but a chapter in the human journey toward truth. As the 20th century unfolded, the quantum revolution became the foundation of modern physics, influencing everything from chemistry and materials science to cosmology and biology. Without it, we would not understand the stars, the processes inside the sun, or the behavior of DNA molecules. It is a revolution that touches every aspect of existence, from the smallest subatomic particles to the largest structures in the universe. And yet, the revolution is not complete. Even today, physicists wrestle with the meaning of quantum mechanics. Interpretations abound: the Copenhagen interpretation, many worlds, pilot wave theories, and others, each offering a different vision of reality. The quantum revolution, then, is not a finished story, but an ongoing dialogue, a continuing quest to understand the secrets of the universe. The meaning of the quantum revolution is both scientific and philosophical. It is scientific in the sense that it provides the most accurate and powerful description of nature we have ever achieved. It is philosophical in that it forces us to reconsider what we mean by reality, knowledge, and truth. It reminds us that the universe is not bound by the limits of human intuition. It teaches us humility in the face of the unknown. The phrase, quantum revolution, captures all of this: the overthrow of classical certainty, the rise of a new probabilistic order, the unlocking of technologies that shape our lives, and the challenge to our deepest ideas about existence. It is a revolution not of politics or nations, but of thought, one that continues to echo through every field of science and every corner of human imagination. The quantum revolution, as it continued to unfold throughout the 20th century, proved itself to be more than just a scientific advancement. It became a profound reimagining of what it means to study and understand the universe. By the 1930s, it was evident that classical physics had been permanently displaced, and quantum theory had taken its place as the new foundation. But what was perhaps even more remarkable was how this new science revealed truths about nature that no human being could ever have anticipated, truths that ran against all common sense and intuition. The meaning of this revolution became increasingly clear. The universe is not built on simple rules that can be visualized like gears in a machine, but on mathematical principles that stretch the limits of human imagination. As experiments grew more refined, the paradoxes of quantum physics only deepened. The famous double-slit experiment, for example, demonstrated the extraordinary dual nature of matter and light. When electrons or photons pass through two slits, they produce an interference pattern like waves, even if fired one at a time. Yet, when an observer attempts to measure which slit the particle passes through, the interference disappears, and the particles behave like tiny bullets. This experiment revealed one of the most unsettling features of quantum mechanics. Observation itself changes the outcome. It is as though the universe withholds its reality until it is observed, leaving physicists and philosophers alike to wonder whether the act of measurement brings the world into being. Such experiments highlighted the philosophical weight of the quantum revolution. No longer could reality be considered fixed, objective, and independent of human inquiry. Instead, it appeared that consciousness, measurement, and interaction were woven into the very fabric of existence. For many scientists, this was deeply troubling, as it suggested that physics had crossed the line from describing the world to participating in it. The revolution was no longer simply about equations. It was about redefining the boundary between observer and observed, between subject and object. As the century progressed, quantum theory extended its reach into new and astonishing territories. One of the strangest consequences of quantum mechanics is entanglement. When two particles interact and become entangled, their properties are linked in such a way that measuring one instantly affects the state of the other, no matter how far apart they are. This phenomenon, which Einstein famously dismissed as spooky action at a distance, challenged the principle of locality, the idea that objects can only influence each other through direct contact or signals traveling at finite speed. Decades later, experiments confirmed that entanglement is real, and it has since become one of the most important resources in the field of quantum information science. The meaning of the quantum revolution, in this respect, is that even the boundaries of space and time can no longer be taken for granted. The universe is connected in ways that defy classical logic. This revolution in thought did not occur without resistance. The debates between Albert Einstein and Niels Bohr throughout the 1920s and 1930s symbolized the struggle to accept the new reality. Einstein, though one of the founding figures of quantum theory, could not accept its indeterminism. He believed there must be hidden variables, unseen mechanisms that would restore determinism and certainty. Bohr, on the other hand, argued that quantum theory was complete as it stood, and that the apparent strangeness was not a flaw, but a reflection of nature itself. Their arguments were not merely academic. They represented two different worldviews, one clinging to the comfort of a predictable universe, the other embracing the strange and counterintuitive. The outcome of these debates shaped not only the direction of physics, but the philosophy of science as a whole. As technology advanced, the practical power of the quantum revolution became undeniable. The development of quantum mechanics gave rise to solid-state physics, which in turn led to the invention of semiconductors and transistors. These components became the building blocks of modern electronics, paving the way for computers, communications, and the digital revolution. Without quantum theory, none of these technologies would exist. Similarly, the principles of quantum mechanics underpin lasers, medical imaging technologies, and much of modern chemistry. The quantum revolution, therefore, is not confined to the blackboards of theoretical physics, but pulses through the circuits of every smartphone, powers the precision of GPS satellites, and illuminates the screens on which billions of people live their daily lives. Yet beyond its technological impact, the quantum revolution continues to inspire wonder and unease in equal measure. The very notion that reality is probabilistic challenges deep human instincts. Throughout history, human beings have sought certainty, whether in religion, philosophy, or science. The quantum world denies such comfort, insisting instead that the universe operates on probabilities, with outcomes that cannot be predicted with certainty. This is not a temporary gap in knowledge, but a permanent feature of existence. Accepting this has been one of the most difficult and most liberating aspects of the revolution. It teaches humility, reminding us that the human mind cannot bend the universe to fit its expectations. Instead, we must bend our expectations to fit the universe. As the 20th century closed, physicists began to dream of harnessing the most bizarre aspects of quantum mechanics for practical use. Quantum computing emerged as a field, promising machines that could exploit superposition and entanglement to perform calculations far beyond the reach of classical computers. Quantum cryptography promised unbreakable communication, secured by the laws of physics themselves. These fields, still in their infancy, suggest that the quantum revolution is far from over. If realized, these technologies could reshape society in ways as profound as the invention of electricity or the rise of the internet. But the revolution is not only about technology and science. It is also about imagination and worldview. Quantum theory has inspired artists, writers, and philosophers who have found in its paradoxes a metaphor for the human condition. The idea that particles can exist in two places at once, or that the act of observation shapes reality, resonates far beyond the laboratory. It speaks to the mystery of consciousness, the fragility of certainty, and the strange beauty of a universe that is more dreamlike than mechanical. In this sense, the quantum revolution has spilled over into culture, influencing not only how scientists see the world but how all of humanity conceives of existence. Still, one of the most striking meanings of the quantum revolution is that it remains unfinished. Even today, more than a century after its beginnings, quantum mechanics has not been fully reconciled with Einstein's theory of relativity. Quantum mechanics rules the microscopic world of atoms and particles, while relativity governs the macroscopic realm of planets and galaxies. The two frameworks, though enormously successful in their domains, remain stubbornly incompatible at the deepest level. The search for a unified theory of quantum gravity, one that can describe black holes and the origins of the universe, is one of the greatest challenges of modern science. Thus, the quantum revolution is ongoing, a revolution still in motion, beckoning us toward new discoveries. The meaning of the quantum revolution, then, is multifaceted. It is a scientific breakthrough that overturns centuries of thought. It is a philosophical shift that forces us to reconsider the nature of reality. It is a technological foundation that underpins modern society and promises even greater advances in the future. And it is a cultural touchstone that reminds us of the mystery and wonder of existence. When we step back and consider the story as a whole, it becomes clear that the quantum revolution is not just about physics. It is about the human spirit. It is about our willingness to question the obvious, to accept paradox, and to search for truth even when that truth defies reason. It shows that progress often comes not from clinging to certainty, but from embracing uncertainty. In a sense, the quantum revolution mirrors the human journey itself, full of mystery, unpredictability, and infinite possibility. From Planck's tentative proposal of energy quanta, to Einstein's photons, to Bohr's atoms, to the wave functions of Schrödinger and the matrices of Heisenberg, and on to the quantum technologies of today, this revolution has unfolded like a grand narrative, a story of discovery that is still being written. It is a story that humbles us, excites us, and challenges us, reminding us that the universe is always deeper, stranger, and more beautiful than we can imagine. The meaning of the quantum revolution is that knowledge is never final, that reality resists simple definition, and that the pursuit of truth is a never-ending journey. It is the recognition that at the heart of matter, at the very foundation of the cosmos, lies not certainty but possibility, not predictability but wonder. The quantum revolution is not just a chapter in science, it is a testament to the limitless curiosity of the human mind and the infinite mystery of the universe it seeks to understand. The story of Niels Bohr begins long before his name became synonymous with the mysteries of the atom and the quantum revolution. It begins in a quiet corner of Copenhagen in the late 19th century, in a world poised on the edge of change. Born in 1885 into a society rich with intellectual ferment and cultural tradition, Bohr's early life was shaped by an environment that encouraged curiosity, learning, and a profound respect for the power of ideas. To understand the man who would later unlock the secrets of the atom, one must first understand the boy who gazed at the world with questioning eyes and an insatiable hunger for knowledge. Niels Henrik David Bohr was born on October 7, 1885, into a family that prized both intellectual engagement and the arts of conversation. His father, Christian Bohr, was a professor of physiology at the University of Copenhagen, renowned for his pioneering work in understanding how oxygen binds to hemoglobin in the blood. Christian Bohr's research placed him at the forefront of the scientific community, and his household was often visited by prominent scholars and thinkers of the time. This meant that from childhood, Niels was immersed in an atmosphere where science was not merely a subject but a living conversation, a pursuit that shaped daily life. His mother, Ellen Adler Bohr, came from a distinguished Jewish family known for their engagement with business and culture. She brought to the family a sensitivity to social issues and a deep appreciation for the humanities. This balance between the scientific rigor of his father and the cultural awareness of his mother created an environment in which young Niels could explore not just equations and experiments, but also the broader meaning of knowledge in human life. It was a household where curiosity was nurtured, and where the boundaries between science, philosophy, and culture were fluid. Growing up in such a setting, Bohr was surrounded by conversations that would spark the imagination of any inquisitive child. His father's colleagues, who often visited their home, included some of the brightest minds in physiology and the natural sciences. These encounters exposed him to the idea that science was not a static body of facts but a dynamic, ongoing quest for understanding. For Niels, this sense of science as a living, breathing enterprise was formative. It sowed the seeds of a mindset that would later enable him to challenge accepted wisdom and to think beyond the confines of tradition. From an early age, Bohr displayed both intellectual brilliance and a reflective, almost philosophical temperament. He attended Gammelholm Latin School, where he excelled in his studies, particularly in mathematics and physics. His teachers recognized his sharp mind and relentless curiosity. Unlike many students who absorbed knowledge passively, Niels constantly questioned what he was taught, probing deeper into the reasons behind formulas and theories. For him, learning was never about memorization. It was about understanding, about uncovering the hidden logic of the world. His passion for science was matched by a love for sport, especially football, which he played with great enthusiasm. In fact, Bohr's younger brother, Harold, went on to become not only a renowned mathematician, but also a member of the Danish national football team. This combination of athleticism and intellectual vigor characterized the Bohr family, reflecting a belief that the mind and body must both be cultivated. Niels himself was less skilled in athletics than Harold, but he brought to the game the same qualities he later brought to science: perseverance, analysis, and a quiet but unshakable determination. As a student, Bohr was fascinated by experiments. He was not content simply to read about theories in textbooks. He wanted to test ideas with his own hands. His first real scientific investigation came during his university years, when he entered a competition sponsored by the Royal Danish Academy of Sciences and Letters. The task was to measure the surface tension of liquids, a complex and delicate problem in physics at the time. Working painstakingly in his father's physiology laboratory, Niels devised ingenious experimental methods, constructing equipment himself when none was available. His study of surface tension was so rigorous and innovative that it won the gold medal in the competition. More importantly, it revealed the qualities that would define him throughout his career: creativity in approach, precision in execution, and an unwillingness to accept limitations imposed by conventional methods. This episode also highlights an essential aspect of Bohr's intellectual character. His deep curiosity was never abstract, but always grounded in practical experimentation. He believed that to truly understand the world, one must engage with it directly through observation and testing. This hands-on approach kept his science anchored in reality, even when his later theories would venture into the most abstract realms of quantum mechanics. During his university years at the University of Copenhagen, Bohr studied under the physicist Christian Christensen, one of the leading Danish scientists of the time. While Christensen's lectures introduced Bohr to advanced theories in physics, it was the young student's independent work that marked him as exceptional. He earned his master's degree in 1909 and his doctorate in 1911 with a thesis on the electron theory of metals. The thesis was notable for its ambitious attempt to explain the properties of metals in terms of the behavior of electrons, a daring step in an era when the electron was still a mysterious and poorly understood entity. Although his thesis did not fully succeed in its goals, it reflected Bohr's unique intellectual style: bold, imaginative, and unwilling to accept half measures. He was not afraid to tackle fundamental problems, even when the available tools seemed inadequate. This intellectual courage would later prove crucial when he developed his atomic model, challenging the limitations of classical physics and venturing into the uncharted territory of quantum theory. Bohr's intellectual curiosity extended far beyond the confines of physics. He was deeply interested in philosophy, particularly in the works of thinkers such as Søren Kierkegaard, the Danish existentialist philosopher. Kierkegaard's emphasis on paradox and the limits of rational thought resonated with Bohr, shaping his philosophical outlook. For Bohr, science was not just about equations and experiments, but also about the deeper meaning of knowledge and the recognition of uncertainty. This philosophical dimension would later become central to his interpretation of quantum mechanics, where he embraced the idea that nature cannot always be described in terms of classical logic. His early life was also marked by a profound humility and modesty, traits that never left him. Despite his brilliance, Bohr was known for his gentle manner, his patience, and his ability to listen deeply to others. He was not a man of grand gestures or dramatic declarations, but of thoughtful reflection and quiet conviction. These qualities made him not only a great scientist but also a great teacher and mentor, someone who inspired loyalty and admiration in those around him. By the time Bohr completed his doctorate, his reputation as a rising star in physics was already established. His curiosity had propelled him beyond the borders of Denmark, drawing him into the wider world of European science. In 1911, he traveled to Cambridge to work under J.J. Thomson, the discoverer of the electron. Although his time with Thomson was not entirely fruitful, it was a crucial step in his journey, for it introduced him to the cutting-edge debates of atomic physics. Later, he moved to Manchester to work with Ernest Rutherford, whose discovery of the atomic nucleus provided the foundation on which Bohr would soon build his revolutionary atomic model. These experiences abroad broadened Bohr's perspective, exposing him to the international scientific community and sharpening his awareness of the great puzzles facing physics. Yet even as he entered this global stage, the roots of his intellectual character remained firmly planted in his early life in Copenhagen. the curiosity instilled in him by his family, the experimental rigor he learned in his father's laboratory, the boldness nurtured in his student research, and the philosophical depth shaped by his engagement with Kierkegaard, all of these elements combined to form the foundation of the scientist who would change the world. In his early life, then, Niels Bohr was not simply preparing for a career in physics, he was developing a worldview, a way of approaching reality that blended science, philosophy, and humanity. His intellectual curiosity was not a passing trait, but a lifelong companion, driving him to seek answers even when none seemed possible, and to embrace paradox rather than shy away from it. These qualities would become the hallmark of his work, enabling him to guide humanity into the quantum age. The later years of Niels Bohr's youth reveal the unfolding of a mind that would one day redefine the limits of human knowledge. Having grown up in an atmosphere that nurtured inquiry, he entered adulthood with the rare combination of experimental skill, theoretical imagination, and philosophical depth. But it was not simply talent that distinguished him, it was his relentless curiosity, his refusal to be satisfied with easy answers, and his willingness to wrestle with the hardest questions of his time. To truly understand the significance of Bohr's early life, one must see how these qualities developed through experiences that shaped his vision of science as both a discipline of precision and an art of interpretation. The atmosphere of Copenhagen during Bohr's formative years cannot be underestimated in shaping his outlook. Denmark at the turn of the 20th century was a nation proud of its cultural heritage, marked by contributions to philosophy, art, and science. The intellectual climate was one in which dialogue and debate flourished, and Bohr absorbed this spirit from his earliest days. His father's connections to the medical and scientific world provided him with exposure to discussions about physiology, physics, and the scientific method. His mother's cultural sensibility grounded him in the awareness that science was not separate from the human story, but a vital part of it. These influences gave him not just curiosity, but a sense of responsibility to approach knowledge with both rigor and humility. Even as a young man, Bohr's personality reflected his unique approach to inquiry. He was never content to accept authority without question. Whether in school or in his later university studies, he developed a reputation for asking questions that probed deeper than the ordinary. Teachers and colleagues soon realized that his curiosity was not disruptive but constructive. He was not seeking to challenge authority for its own sake, but to uncover the truth hidden beneath assumptions. This approach, which was evident even in his teenage years, foreshadowed the way he would later challenge the classical foundations of physics itself. One telling example of Bohr's curiosity came in his fascination with the fine details of natural phenomena. He had a remarkable patience for observation, whether it was the motion of fluids, the behavior of light, or the complexities of mathematical formulas. He would spend long hours not just performing experiments, but reflecting on what they meant. To him, science was not a race for results, but a dialogue with nature, a conversation that demanded attentiveness and humility. This attitude set him apart from many of his contemporaries, who were often more focused on practical outcomes than on the deeper implications of their findings. When he undertook his early research on the surface tension of liquids, Bohr's dedication to the smallest details revealed not only his skill as an experimentalist, but also his intellectual perseverance. At a time when many young scientists would have been daunted by the challenge of constructing delicate apparatus, he approached the task with determination, fashioning his own instruments when necessary. The fact that he was willing to spend months refining measurements that others might have dismissed as too difficult speaks to his belief that every detail mattered. This same meticulousness would later characterize his development of the atomic model, where he worked through countless calculations and scenarios before arriving at a structure that satisfied both experimental data and theoretical insight. But Bohr's intellectual curiosity was never limited to technical matters. His deep engagement with philosophy during his university years left a profound mark on him. He was particularly drawn to the writings of Kierkegaard, whose exploration of paradox, uncertainty, and the limits of rational thought resonated with Bohr's own reflections. Kierkegaard's insistence that truth often lies beyond the grasp of simple logic helped shape Bohr's openness to the strange and counterintuitive implications of quantum mechanics. For him, philosophy and science were not separate domains, but complementary approaches to the same quest for understanding. Where science provided the tools of measurement and prediction, philosophy offered the wisdom to interpret the meaning of those findings in a broader context. This blending of science and philosophy gave Bohr a distinctive voice among his peers. Whereas many physicists approach problems with narrow technical focus, Bohr brought a breadth of vision that sought not only to solve puzzles, but to understand their significance. Even in his earliest papers, he demonstrated a willingness to ask what the results implied about the nature of reality, not merely what they meant in terms of equations. This habit of reflection would later culminate in his famous principle of complementarity, a concept that revealed the philosophical depth of his approach to quantum mechanics. Equally important in Bohr's development was his temperament. Despite his brilliance, he was remarkably modest and approachable. He preferred dialogue to monologue, discussion to declaration. As a student, he would often test his ideas by talking them through with friends and colleagues, listening carefully to their responses, and refining his views accordingly. This openness to others' perspectives made him not only a great scientist, but also a great mentor, a quality that would later define his leadership of the Institute for Theoretical Physics in Copenhagen. But even in his youth, this collaborative spirit was evident. He understood that science was not a solitary endeavor, but a collective journey, enriched by the contributions of many minds. Bohr's early curiosity also expressed itself in his willingness to cross disciplinary boundaries. While his formal training was in physics, he drew insights from physiology, mathematics, and philosophy. This interdisciplinarity was partly the legacy of his family background, but it was also the result of his own restless mind. He was never satisfied with staying within the confines of one field. He sought connections, analogies, and broader patterns. This holistic vision would later allow him to see possibilities that others missed, such as the radical step of quantizing electron orbits in the atom. The years he spent abroad after completing his doctorate were crucial in expanding his horizons. His time at Cambridge, though not particularly fruitful in terms of immediate results, exposed him to the forefront of atomic research under J.J. Thomson. More importantly, his subsequent work with Ernest Rutherford in Manchester brought him into direct contact with one of the most brilliant experimentalists of the age. Rutherford's discovery of the atomic nucleus in 1911 provided the spark that ignited Bohr's imagination. Where others saw a puzzle, Bohr saw a challenge to be solved through bold new thinking. It was his curiosity, nurtured since childhood, that gave him the courage to depart from classical ideas and to envision a new structure of the atom that defied expectation. Yet even as he entered this stage of groundbreaking discovery, Bohr's early life remained a guiding force in his character. The humility instilled in him by his upbringing, the patience learned from his early experiments, and the philosophical depth shaped by Kierkegaard all combined to form a scientist unlike any other. His intellectual curiosity was not just a trait but a lifelong practice, a way of engaging with the world that defined his identity. In many ways, Bohr's early life is a microcosm of the larger story of the quantum revolution itself. Just as physics had to move beyond the certainties of classical mechanics and embrace paradox, so too did Bohr, as a young man, learn to embrace uncertainty and complexity in his quest for truth. His early experiences taught him that knowledge is never final, that every answer raises new questions, and that the pursuit of science requires both rigor and imagination. When looking back on Bohr's early years, one sees not only the making of a great physicist, but also the unfolding of a worldview that would later influence generations. His intellectual curiosity, grounded in the nurturing environment of his family, enriched by his education, and expanded by his travels, became the foundation of his genius. It was this curiosity that drove him to challenge the accepted wisdom of his time, to risk bold new ideas, and ultimately to open the door to the quantum age. Thus, the significance of Bohr's early life lies not only in the details of his upbringing, but in the way those experiences shaped his intellectual character. He emerged from his youth not only as a brilliant physicist, but as a thinker who understood that science is as much about questions as it is about answers, as much about mystery as it is about clarity. His curiosity was the thread that connected the boy in Copenhagen to the man who revealed the secret of the atom. It was, in the end, the defining quality of his life and the key to his enduring legacy. The story of the Bohr model of the atom begins at a time when physics itself was standing at the edge of a precipice, teetering between the familiar certainties of the 19th century and the strange new possibilities of the 20th. By the early 1910s, scientists had already discovered that atoms, once thought to be indivisible, contained internal structure. The electron had been identified by J.J. Thomson in 1897, and just over a decade later, Ernest Rutherford had demonstrated through his famous gold foil experiment that atoms possessed a tiny, dense nucleus at their core. Yet, despite these discoveries, the actual architecture of the atom remained an enigma. What held electrons in place around the nucleus? Why didn't they spiral inward, as classical physics demanded? How could atoms, which formed the fabric of all matter, remain stable in a world where known laws of motion predicted their collapse? Into this landscape of uncertainty stepped Niels Bohr, armed not only with equations and experimental data, but with the courage to imagine something radically different. Bohr's breakthrough did not come in isolation. He was a product of his time, and his thinking drew upon a convergence of ideas that had been developing in physics over several decades. The puzzle of atomic structure was already a pressing concern, and many brilliant minds had attempted to resolve it. Thomson's early, plum pudding model, which envisioned electrons embedded like raisins in a diffuse cloud of positive charge, had been overturned by Rutherford's nuclear model. Yet Rutherford's model, elegant as it was, left one crucial question unanswered. If electrons orbited the nucleus like planets around the Sun, as Rutherford proposed, then electromagnetic theory predicted that these accelerating charges would radiate energy continuously. Within a fraction of a second, the electrons should lose their energy, spiral inward, and collapse into the nucleus. Clearly, atoms were not collapsing all around us, so something was missing in the understanding. At this juncture, Bohr's genius lay in seeing beyond the limitations of classical theory and daring to incorporate the strange new insights that were emerging from the quantum revolution. Max Planck in 1900 had introduced the radical idea that energy is quantized, existing in discrete packets called quanta. Albert Einstein in 1905 had extended this concept to light, explaining the photoelectric effect by proposing that light itself was made of quanta, later called photons. These ideas were revolutionary but deeply unsettling, for they undermined the continuous, predictable universe of Newton and Maxwell. Yet, they also offered a possible solution to the riddle of the atom. Bohr recognized that the key to atomic stability might lie not in smooth classical orbits, but in quantized states of energy. When Bohr arrived in Manchester to work under Rutherford in 1912, he was immersed in an environment of experimental discovery and theoretical challenge. Rutherford had just unveiled the nuclear atom, but the task of explaining how electrons arranged themselves around the nucleus was still unresolved. Bohr began to study this problem with a bold perspective, merging Rutherford's nuclear concept with Planck's quantum theory. He proposed that electrons did not orbit the nucleus in arbitrary paths, but instead occupied specific, quantized orbits. These orbits were stable, not because of any mysterious force, but because the electrons in them did not radiate energy, contrary to classical expectations. Only when an electron jumped from one orbit to another would it emit or absorb a quantum of energy, corresponding precisely to the difference between the energy levels. This proposal, introduced in Bohr's 1913 trilogy of papers, was nothing short of revolutionary. It redefined the very nature of the atom and introduced the concept of the quantum leap, the discontinuous jump of an electron between energy states. This was not merely a modification of existing theory, it was a conceptual transformation. The atom was no longer a miniature solar system governed solely by Newtonian mechanics. It was a strange, quantized world where stability arose from discrete states and radiation was emitted in bursts rather than in continuous waves. The daring simplicity of the model was breathtaking. It resolved the paradox of atomic stability, explained the discrete spectral lines observed in hydrogen, and provided a framework for understanding the inner workings of matter. Perhaps the most striking success of Bohr's model was its explanation of the hydrogen spectrum. For decades, scientists had puzzled over why hydrogen emitted light at specific wavelengths, forming distinct spectral lines. These patterns had been recorded with precision but remained unexplained by classical theory. Bohr demonstrated that his quantized orbits predicted these lines exactly. When an electron in hydrogen jumped from a higher orbit to a lower one, the energy released corresponded to the precise wavelength of light observed in experiments. The agreement between theory and observation was so exact that it left little doubt about the validity of his approach. For the first time, the strange new world of quantum physics provided a clear explanation for phenomena that had baffled generations. Bohr's model did more than solve a technical problem. It represented a new way of thinking about nature. It suggested that the universe at its most fundamental level did not obey the continuous, deterministic laws that had governed physics since the time of Newton. Instead, it operated according to principles of discontinuity and probability, where particles could occupy only certain states and where change occurred in sudden leaps. This was a profound departure from the mechanical worldview of the 19th century, and it signaled the birth of a new physics that would dominate the 20th. The reception of Bohr's model was mixed at first. Some physicists were skeptical of its radical departure from classical ideas, while others recognized immediately that it marked a turning point. The younger generation of scientists, including figures like Werner Heisenberg, Wolfgang Pauli, and Paul Dirac, saw in Bohr's ideas the seeds of a deeper theory that would later blossom into quantum mechanics. For them, Bohr's willingness to embrace paradox and break free from classical constraints was an inspiration. They recognized that the future of physics lay not in clinging to old certainties, but in daring to imagine new possibilities. What made the Bohr model so powerful was not only its success in explaining hydrogen, but also its suggestive potential for more complex atoms. While the model encountered difficulties, when applied beyond hydrogen and helium, its conceptual framework laid the groundwork for future theories. It opened the door to the idea of quantized angular momentum, to the concept of energy levels and shells, and to the understanding of atomic structure that underpins modern chemistry and physics. Even as refinements were needed, the core insight, that electrons occupy discrete energy states, remained a permanent feature of quantum theory. Bohr's work also carried philosophical implications that extended far beyond physics. It challenged the very notion of reality as continuous and predictable. If electrons could only exist in certain states, and if transitions between them occurred in leaps, then the fabric of nature itself was quantized. This raised profound questions about determinism, causality, and the limits of human knowledge. Bohr himself was deeply aware of these implications, and he would later develop his principle of complementarity as a way of grappling with them. But even in 1913, with his first model of the atom, he had already shown that physics was no longer simply about describing the visible world. It was about uncovering a hidden order that defied common sense, yet revealed deeper truths. In recounting the story of the Bohr model, one must not lose sight of the personal courage it required. To propose such a radical idea in the early 20th century was no small matter. The authority of classical physics was immense, and many scientists were reluctant to embrace concepts that seemed to violate its principles. Bohr's readiness to trust his intuition, to follow the logic of quantum theory, even when it conflicted with established wisdom, is a testament to his intellectual bravery. He was not reckless, but he was willing to take calculated risks, guided by both mathematics and experimental evidence. In doing so, he set an example of scientific creativity that continues to inspire to this day. As the model gained acceptance, its impact spread far beyond the walls of physics laboratories. It influenced chemistry by providing a theoretical basis for the periodic table and the behavior of elements. It influenced technology by laying the foundation for quantum mechanics, which would eventually give rise to semiconductors, lasers, and countless modern innovations. And it influenced philosophy by forcing thinkers to reconsider the meaning of knowledge, reality, and truth in a quantized universe. In all these ways, the Bohr model was more than a scientific advance, it was a turning point in human understanding. The year 1913, when Bohr published his trilogy of papers, can thus be seen as the beginning of the quantum revolution in earnest. What Planck and Einstein had hinted at, Bohr made tangible and concrete in the structure of the atom. He showed that quantum theory was not an abstract mathematical trick, but a real feature of nature, shaping the very building blocks of matter. The impact of this realization reverberated through the scientific community and beyond, heralding a new era in which the secrets of the atom would be unlocked and harnessed. Thus, the story of the Bohr model is not just the story of an equation or a diagram, it is the story of a moment when human thought took a leap as dramatic as the quantum jumps it described. It is the story of how a young Danish physicist, drawing upon the insights of his predecessors and the courage of his convictions, opened a new chapter in the history of science, and it is the story of how the atom, once shrouded in mystery, revealed its secrets in the language of quanta, forever changing our vision of the universe. The publication of Niels Bohr's trilogy of papers in 1913 did more than introduce a new atomic model, it signaled the beginning of a profound transformation in the way scientists thought about nature. In the decades that followed, Bohr's ideas would be tested, challenged, refined, and ultimately expanded into the full framework of quantum mechanics. Yet the essence of his model, the bold proposal that electrons occupied quantized orbits and that energy was emitted or absorbed only in discrete jumps, remained a cornerstone of modern physics. To fully appreciate the significance of this development, one must follow not only the immediate successes of the Bohr model, but also its limitations, its philosophical implications, and its lasting influence on science and society. In the years immediately after 1913, the Bohr model quickly became a central topic of research and debate. Its ability to explain the hydrogen spectrum so precisely gave it an undeniable credibility, and physicists across Europe and America began to study its consequences. Textbooks that had once described atoms as indivisible, or as classical miniature solar systems, now included diagrams of quantized electron orbits. For students encountering physics at this time, Bohr's atom became the new icon of scientific progress, a symbol of how imagination and mathematics could illuminate the unseen structure of reality. In lecture halls and laboratories, the language of energy levels and quantum jumps entered everyday discourse. Yet as powerful as it was, the model was not without difficulties. When applied to atoms more complex than hydrogen, the predictions became less accurate. The spectra of helium and heavier elements could not be explained in detail by Bohr's simple picture of circular orbits. Moreover, certain phenomena, such as the fine structure of spectral lines or the Zeeman effect in magnetic fields, required refinements that went beyond the original model. These shortcomings were not signs of failure, but rather indications that Bohr's idea was only the first step toward a deeper theory. The model provided a framework, but it was clear that a more comprehensive approach would be needed to fully capture the complexities of atomic behavior. Bohr himself was fully aware of these limitations. He did not cling stubbornly to his model, but instead encouraged the exploration of new approaches. His attitude was one of openness, guided by the belief that science must evolve in response to evidence. This humility distinguished him from some contemporaries who sought finality in their theories. For Bohr, the 1913 model was never the end of the story. It was the beginning of a dialogue with nature that would lead to the more sophisticated theories of quantum mechanics. His willingness to embrace uncertainty and paradox would become one of his defining intellectual traits. The philosophical implications of Bohr's model began to resonate far beyond physics. If electrons did not move in continuous paths, but instead occupied discrete states, then the very notion of continuity in nature was under question. The atom was no longer a smooth, mechanical system, but a quantized structure governed by rules that defied classical intuition. This raised profound questions about determinism. In Newton's universe, given enough information, one could in principle predict the motion of every particle with certainty. In Bohr's universe, however, the future of an electron could not be described with such precision. It could only be said to occupy certain allowed states and to leap between them unpredictably. The philosophical shift was immense, forcing thinkers to reconsider long-held assumptions about causality and reality. It was within this intellectual ferment that Bohr began to articulate what would later become his principle of complementarity. While this principle would not be fully developed until the late 1920s, its roots can be traced back to his reflections on the paradoxical nature of the atom. The Bohr model already contained a tension between particle-like and wave-like descriptions of matter. Electrons were treated as particles occupying orbits, yet their behavior could only be explained by invoking quantization, a concept rooted in wave phenomena. Rather than seeking to eliminate this contradiction, Bohr accepted it as a feature of reality. This openness to paradox distinguished his thinking and laid the foundation for the philosophical depth of quantum mechanics. Meanwhile, the impact of the Bohr model on chemistry was profound. For the first time, scientists had a theoretical framework that explained why elements exhibited certain chemical properties. The arrangement of electrons in quantized shells around the nucleus provided a natural explanation for the periodic table, which had been empirically organized since Mendeleev's time but lacked a theoretical basis. Bohr's model showed why elements in the same column of the table shared similar properties. Their outermost electrons occupied similar energy levels. This connection between physics and chemistry represented a triumph of unification, showing that the laws of the microscopic world could explain the macroscopic patterns of the natural world. The cultural resonance of the Bohr model was equally striking. In newspapers and popular books, the atom became a symbol of modernity, a mysterious and powerful entity that science was finally beginning to unravel. The image of electrons circling a nucleus like planets around the sun became iconic, even if later refinements would show it to be oversimplified. For the general public, the Bohr atom captured the imagination, embodying both the promise of scientific progress and the strangeness of a universe that no longer obeyed common sense. In classrooms and laboratories alike, the quantized atom became a gateway into the wonders of the quantum world. As the 1920s unfolded, the limitations of the Bohr model spurred further advances. The old quantum theory, of which Bohr's model was the centerpiece, gradually gave way to the new quantum mechanics developed by Heisenberg, Schrödinger, and Dirac. These new formulations replaced the image of electrons in orbits with the more abstract mathematics of wave functions and probability. Yet Bohr's influence was everywhere in this transition. His insistence on quantization, his willingness to accept paradox, and his philosophical reflections shaped the thinking of the younger generation who built the full edifice of quantum mechanics. Indeed, many of them, including Heisenberg, worked directly with Bohr at his Copenhagen Institute, where the intellectual atmosphere fostered by Bohr became a crucible for the quantum revolution. The legacy of the Bohr model can thus be measured not only in its direct successes, but also in its role as a catalyst for deeper understanding. By daring to break free from classical constraints, Bohr opened a path that others would follow to even greater discoveries. His model demonstrated the power of combining experimental evidence with theoretical imagination, of balancing boldness with humility. It showed that science advances not by clinging to established truths, but by questioning them, by embracing the unknown and the counterintuitive. Beyond its scientific and philosophical impact, the Bohr model also carried practical consequences. The understanding of atomic structure that it initiated eventually led to technologies that transformed the modern world. Quantum mechanics, built upon the foundation laid by Bohr, became the basis for semiconductors, computers, lasers, and medical imaging technologies. While Bohr himself could not have foreseen these applications in 1913, his model was the spark that ignited a chain of developments leading to the technological landscape of the 21st century. In this sense, his work belongs not only to the history of science, but also to the history of human civilization. Reflecting on the Bohr model a century later, it is easy to see both its limitations and its brilliance. It did not provide the final description of the atom, but it marked the turning point at which physics embraced the quantum. It did not resolve all questions, but it framed them in a way that made further progress possible. Above all, it demonstrated the power of imagination guided by evidence, the willingness to envision a reality that defies intuition but reveals truth. In this respect, Bohr's model remains not just a scientific theory, but a symbol of the human capacity to transcend the familiar and enter new realms of understanding. The quantum leap that Bohr described for electrons was mirrored by the intellectual leap he himself made in 1913. Just as electrons jump from one orbit to another without traversing the space between, so too did physics jump from the classical to the quantum world in a discontinuous transformation. It was not a gradual evolution but a sudden change in perspective, a redefinition of the possible. In this sense, Bohr's model was more than a scientific contribution, it was a metaphor for the evolution of human thought itself, a reminder that progress often comes in leaps rather than in smooth continuity. Thus, the Bohr model of the atom stands as one of the great landmarks in the history of science. It bridged the gap between classical physics and quantum mechanics, provided a framework for understanding atomic structure, and inspired generations of scientists to explore the mysteries of the quantum world. It exemplifies the courage to question, the humility to revise, and the creativity to imagine beyond the limits of the known. In telling its story, we are reminded not only of the genius of Niels Bohr, but also of the enduring spirit of inquiry that drives humanity forward. Niels Bohr's role in shaping the foundations of quantum mechanics cannot be understood merely as the contribution of another physicist working on equations and experiments. It was far deeper than that. Bohr became a guide, a philosopher, and a mentor during a time when physics was undergoing its most radical transformation. The early 20th century was an age of uncertainty, where the certainties of Newtonian mechanics and Maxwell's electrodynamics were giving way to strange new principles that seemed to defy common sense. Out of this chaos emerged quantum mechanics, a framework that would forever change science. Bohr was not only at the heart of this revolution, but also the thinker who gave it meaning through his principle of complementarity, which shaped the way physicists understood the strange dual nature of the quantum world. By the mid-1920s, it was clear that the old quantum theory, including Bohr's own atomic model, was insufficient. The success of the Bohr model with hydrogen could not be extended neatly to heavier atoms, and the growing evidence of wave-particle duality called for a deeper rethinking. In 1924, Louis de Broglie proposed that particles like electrons also had wave properties, an idea that was startling but soon confirmed experimentally. Just 2 years later, Erwin Schrödinger developed wave mechanics, describing electrons not as tiny planets circling a nucleus, but as wave functions spread out in space. At nearly the same time, Werner Heisenberg introduced matrix mechanics, a radically abstract mathematical formulation that dispensed with visual models altogether. Quantum physics had suddenly split into different schools of thought, each strange in its own way, each incomplete on its own. It was at this critical moment that Bohr's influence became most decisive. He recognized that both Schrödinger's and Heisenberg's approaches were not rivals, but complementary descriptions of the same underlying reality. Heisenberg's work highlighted the importance of measurable quantities and led directly to his uncertainty principle, which declared that one cannot know both the position and momentum of a particle with absolute precision. Schrödinger's wave mechanics, on the other hand, provided intuitive pictures of electrons as standing waves in orbitals. These two pictures seemed irreconcilable. How could the electron be both a particle with measurable properties and a wave spread across space? Bohr's response to this paradox was not to choose one picture over the other, but to accept both, introducing the principle of complementarity in 1927. According to this principle, the wave and particle aspects of quantum objects are not contradictory, but complementary. They are different perspectives that cannot be observed simultaneously, but are both necessary to fully describe reality. Just as light can appear as a wave in diffraction experiments and as a particle in the photoelectric effect, so too could electrons and other quantum entities display dual natures depending on the experimental setup. Complementarity thus became a philosophical foundation for quantum mechanics, teaching physicists that reality at the quantum level resists description in classical terms and requires new modes of thought. The significance of complementarity extended beyond physics. It was not only a scientific idea, but also a profound philosophical statement about the limits of human knowledge. Bohr argued that our descriptions of nature are shaped by the language and concepts available to us, and at the quantum level, these classical concepts break down. We cannot speak of an electron having both a definite position and momentum simultaneously, because the very act of measurement defines what aspect of reality we are observing. This was not simply a technical limitation, but a fundamental feature of nature. In this sense, complementarity was Bohr's way of reconciling the apparent contradictions of quantum mechanics while offering a coherent philosophical interpretation. The importance of Bohr's role was highlighted at the famous Solvay Conference of 1927, where the world's greatest physicists gathered to debate the meaning of quantum theory. It was here that Albert Einstein, who never accepted the indeterminism of quantum mechanics, confronted Bohr in a series of intellectual duels. Einstein's repeated challenges, often framed as thought experiments, aimed to demonstrate that quantum mechanics was incomplete. Bohr, with his calm but relentless reasoning, countered each objection, showing that quantum theory, strange as it seemed, was consistent and complete within its own framework. These debates became legendary, symbolizing the clash between determinism and probability, between classical certainty and quantum ambiguity. Though Einstein's doubts lingered, most of the physics community came to side with Bohr's interpretation, which laid the groundwork for what became known as the Copenhagen interpretation of quantum mechanics. At the heart of this interpretation was Bohr's insistence that physics is not about uncovering reality in itself, independent of observation, but about describing phenomena as they appear under specific experimental conditions. For Bohr, there was no meaning in speaking of quantum objects without reference to measurement. This did not mean that reality did not exist, but rather that our access to it was mediated by the act of observation. Such a view was radical, for it implied that knowledge itself was participatory, shaped by the interaction between observer and system. This perspective influenced not only physics but also fields as diverse as philosophy, psychology, and even art, where the themes of ambiguity and duality found resonance. Bohr's Copenhagen Institute became the intellectual center of this new way of thinking. Young physicists from across Europe and beyond flocked to work with him, finding in Copenhagen not just a place of research but a community of dialogue. Bohr's style of mentorship was unique. He engaged his students and colleagues in deep conversations, often posing questions rather than giving answers, encouraging them to think for themselves. Figures such as Heisenberg, Pauli Dirac, and Landau all spent time under his guidance, and many later became giants of 20th century physics. The collaborative atmosphere Bohr created ensured that Copenhagen became the birthplace of modern quantum mechanics, a place where equations and experiments were infused with philosophical reflection. The lasting importance of Bohr's contribution lies not just in his principle of complementarity, but in his broader vision of science. He taught that the role of the physicist is not to impose classical ideas on the quantum world, but to adapt our concepts to fit the evidence. He reminded his peers that paradox is not failure but a sign of progress, pointing toward deeper truths. By embracing, rather than resisting, the strangeness of quantum mechanics, Bohr helped ensure that the theory could flourish into a coherent and immensely successful framework, one that underpins much of modern technology. In retrospect, the foundations of quantum mechanics bear the imprint of Bohr's intellectual style as much as his technical insights. He was cautious yet bold, skeptical yet open-minded, modest yet firm in defending ideas he believed essential. His principle of complementarity continues to resonate today, not only as a key concept in physics, but as a metaphor for human understanding in general. It reminds us that reality can be richer than any single perspective, and that truth often lies in the interplay of seemingly opposing views. Thus, Bohr's role in shaping the foundations of quantum mechanics was not just to provide solutions, but to set the stage for an entire worldview. Through his principle of complementarity, his leadership in Copenhagen, and his philosophical depth, he gave quantum mechanics its soul. Without him, the theory might have remained a set of equations. With him, it became a way of seeing the universe, one that continues to challenge and inspire scientists and thinkers alike. Niels Bohr's contributions to science cannot be fully appreciated without recognizing the profound influence he had on the training and nurturing of a new generation of physicists. Beyond his pioneering work in quantum theory and the atomic model, Bohr played the role of a teacher, mentor, and leader who helped shape the intellectual culture of modern physics. His institute in Copenhagen became more than a research center. It was the heart of a global scientific community where ideas flowed freely, young minds were encouraged, and collaboration was valued as highly as individual genius. In many ways, Bohr's legacy as a builder of scientific networks is as enduring as his theoretical discoveries. From the earliest days of his career, Bohr understood that the advancement of physics required more than equations and experiments. It demanded a supportive environment where students and colleagues could test their thoughts, share doubts, and refine theories together. When the Institute for Theoretical Physics opened in Copenhagen in 1921 under his direction, it quickly became a magnet for brilliant young scientists from across Europe and beyond. Unlike traditional institutions, Bohr's institute had no rigid hierarchy. Instead, it cultivated an atmosphere of openness where everyone, from the youngest student to the most distinguished professor, could participate in discussions. This openness reflected Bohr's own personality, marked by humility, curiosity, and a genuine respect for differing perspectives. The list of physicists who passed through Copenhagen reads like a roll call of 20th century science: Werner Heisenberg, Wolfgang Pauli, Paul Dirac, Lev Landau, George Gamow, and many others. For many of them, their time with Bohr shaped their careers and their outlook on science. Heisenberg, for example, developed much of matrix mechanics while working closely with Bohr, and their late-night conversations were legendary for their intensity and depth. Pauli, known for his sharp wit and critical eye, found in Bohr a mentor who balanced his criticism with encouragement. For young minds, Copenhagen was a place where radical ideas could be debated without fear of dismissal. Bohr's insistence on dialogue meant that even the most unconventional thoughts were given serious attention, provided they were expressed with clarity and rigor. Bohr's mentorship style was unique. He often asked more questions than he answered, gently guiding his students toward their own discoveries rather than imposing his views. His conversations were famously long and sometimes difficult, filled with pauses as he carefully weighed each word. Yet this very style forced his students to think more deeply about their own assumptions and to refine their ideas with greater precision. Many later recalled that these exchanges were transformative, shaping not just their research, but their approach to scientific inquiry itself. In this way, Bohr helped cultivate not only great physicists, but also a culture of scientific humility and collaboration. He rejected the notion of the solitary genius working in isolation. Instead, he believed that science advanced best when it was a collective enterprise where individuals supported each other in a shared search for truth. This philosophy was especially important in a time when nationalism and political divisions threatened to fracture the international scientific community. Bohr's Institute became a rare space where scientists of different nationalities could work side by side, bound not by politics but by their common pursuit of knowledge. This internationalism became even more significant during the turbulent decades of the 1930s and 1940s. As fascism rose in Europe, and many Jewish scientists were forced to flee their homelands, Bohr and his institute provided refuge and support. He welcomed exiled physicists to Copenhagen, giving them not only work but also a sense of belonging in a community that valued their talents. When war eventually engulfed Europe, Bohr's commitment to the international spirit of science only deepened. After escaping Nazi-occupied Denmark in 1943, he became an advocate for cooperation between nations in the post-war era, arguing that the discoveries of science should be used to promote peace rather than division. In the classroom and seminar hall, Bohr's influence extended even further. He was not content with students merely memorizing theories. He wanted them to wrestle with the philosophical implications of quantum mechanics, to confront the paradoxes and ambiguities rather than ignore them. For Bohr, physics was not just a technical discipline, but a way of thinking about the nature of reality itself. This insistence on the broader meaning of science shaped a generation of physicists who carried forward not only his theories, but also his spirit of inquiry. Bohr's impact on education was also reflected in the way he helped establish research collaborations and conferences that encouraged dialogue across borders. He was instrumental in bringing young scientists together, creating networks that allowed knowledge to spread rapidly and ideas to be tested in a truly global arena. The annual gatherings and informal exchanges at his institute became models for later scientific organizations, demonstrating that progress in science often depends on the free exchange of ideas across cultures and disciplines. In the post-war years, Bohr continued to advocate for the role of education and international cooperation. He emphasized that the discoveries of nuclear physics carried both immense promise and grave responsibility. In his writings and public addresses, he urged governments to share knowledge openly and to use science as a bridge between nations rather than a weapon of competition. This vision of science as a universal human endeavor, transcending political boundaries, was one of his most important legacies. The ripple effects of Bohr's educational and mentoring efforts can still be felt today. Many of the scientists he trained or influenced went on to establish their own institutes, spreading the collaborative culture he had fostered. The principles he embodied, humility, openness, dialogue, and internationalism, became hallmarks of the modern scientific community. In many ways, the global networks of research and cooperation that drive science today can trace their roots back to the intellectual community that Bohr nurtured in Copenhagen. To speak of Bohr, therefore, is not only to speak of quantum mechanics and complementarity, but also to recognize his role as a builder of people, ideas, and communities. He understood that the greatest discoveries are rarely made alone and that science, at its best, is a shared journey of questioning and discovery. His institute stood as a beacon of this belief, a place where young minds could flourish, and where the boundaries of knowledge were pushed forward not by rivalry, but by collective effort. In this way, Niels Bohr helped shape not just the science of his time, but the very culture of physics. He gave the world not only theories of atoms and principles of complementarity, but also a living model of how science should be practiced, with openness, humility, and a commitment to the common good. His role as an educator and mentor ensured that his influence would endure far beyond his own lifetime, carried forward in the lives and work of those he inspired. Niels Bohr's name is often linked with the birth of quantum mechanics, but his story is also deeply woven into the dramatic history of nuclear research in the 20th century. As the atomic nucleus became a focus of scientific exploration in the 1930s, Bohr's insights helped pave the way for discoveries that would change the course of human history. His involvement with nuclear fission, and later with the Manhattan Project, revealed a man torn between the exhilaration of scientific progress and the profound ethical dilemmas it created. For Bohr, the atom was not only a scientific frontier, but also a symbol of humanity's responsibility to use knowledge wisely. His lifelong efforts to promote openness and cooperation in atomic research reflected a vision of science as a force for peace rather than destruction. The breakthrough moment came in 1938, when German scientists Otto Hahn and Fritz Strassmann discovered nuclear fission, the splitting of the uranium nucleus. When news of this reached the wider scientific community, it was Bohr who played a key role in clarifying its significance. In early 1939, Bohr traveled to the United States and presented the findings at a physics conference, electrifying the audience with the realization that enormous amounts of energy could be released by splitting atoms. Bohr himself, working with his student John Wheeler, developed a theoretical model of fission that explained the mechanism by which neutrons could trigger a chain reaction. Their liquid drop model of the nucleus showed how the nucleus could be thought of as a charged liquid drop that could elongate, oscillate, and eventually split apart when disturbed. This work became one of the theoretical cornerstones of nuclear physics. As the world slid closer to war, the implications of nuclear fission became clear. If a chain reaction could be controlled, it might produce a new source of energy, but if it were uncontrolled, it could lead to a weapon of unprecedented power. When World War II began, the possibility that Nazi Germany might develop such a weapon gave urgency to atomic research in Allied countries. Bohr, who was Danish and of partly Jewish descent, soon found himself in great danger after Germany occupied Denmark in 1940. Despite surveillance and pressure, he continued his scientific work quietly, but by 1943, the situation had grown too perilous. With the help of the Danish resistance, Bohr escaped to Sweden, and from there he was flown in a dramatic secret mission to Britain, eventually arriving safely in the United States. In the U.S., Bohr was brought into contact with the Manhattan Project, the massive Allied effort to build an atomic bomb. Although he contributed ideas to the project, his role was never primarily technical. Instead, Bohr's greatest contribution was his vision of what nuclear energy meant for the future of humanity. He warned that once nuclear weapons were created, they could not be uninvented, and the only way to ensure peace was through openness and international cooperation. In his discussions with both British and American leaders, including Winston Churchill and Franklin Roosevelt, Bohr urged them to consider sharing information with the Soviet Union to prevent a dangerous arms race after the war. He believed that secrecy would breed mistrust, while openness could create the foundation for lasting peace. Bohr's appeals, however, were met with suspicion. Churchill in particular distrusted Bohr's idealism, fearing that sharing nuclear knowledge would strengthen the Soviets. Bohr's attempts to influence policy during the war were thus largely unsuccessful, yet his warnings proved prophetic. After the war ended, the United States and the Soviet Union quickly entered into a nuclear arms race, and the Cold War era was defined by the threat of mutually assured destruction. Bohr, though disappointed that his advice had not been heeded, continued to advocate tirelessly for peaceful cooperation. After returning to Denmark, Bohr became a vocal supporter of the peaceful uses of atomic energy. He promoted nuclear power not as a weapon, but as a potential solution to humanity's energy needs. His writings and speeches stressed that scientific progress must be accompanied by moral responsibility, and that the international community must find ways to control nuclear technology collectively. In 1950, he published an open letter to the United Nations, calling for the free exchange of scientific knowledge and the creation of international frameworks to regulate nuclear research. His message was that the same science which had produced the bomb could, if guided by wisdom, be used to benefit humanity. Bohr's influence also extended to the creation of institutions that embodied this vision. He was instrumental in shaping the ideas that led to the establishment of the International Atomic Energy Agency (IAEA), which sought to oversee the safe use of nuclear technology worldwide. He also supported the founding of CERN, the European Nuclear Research Organization, which became a model of international scientific cooperation. These institutions reflected Bohr's belief that science must transcend political divisions, and that only through global collaboration could the dangers of nuclear weapons be managed. His dual role as both a contributor to nuclear science and a moral critic of its misuse made Bohr a unique figure in the history of the atomic age. On the one hand, his theoretical work on nuclear structure and fission had helped make the bomb possible. On the other, he consistently tried to steer the world away from the destructive path that the bomb represented. This paradox mirrored the duality at the heart of his complementarity principle. Just as particles and waves represented two sides of reality, so too did nuclear energy embody both promise and peril. It was up to humanity to decide which aspect would dominate. Bohr's legacy in this domain is not measured in equations or experiments alone, but in the values he championed. He embodied the idea that scientists are not mere technicians solving puzzles, but citizens of the world whose work carries profound social consequences. His insistence on openness, dialogue, and shared responsibility resonates strongly in today's world, where nuclear proliferation, energy crisis, and global cooperation remain pressing issues. In reflecting on his role, one sees a man deeply aware of both the power and the fragility of human knowledge. He had helped unlock the secret of the atom, but he never stopped reminding others that this secret came with an obligation to use it wisely. His life thus stands as a reminder that science, though capable of breathtaking achievements, must always be guided by conscience. The story of Niels Bohr does not end with his lifetime achievements, for his influence has continued to ripple across generations in science, philosophy, and society. Few figures in modern history have left behind a legacy that bridges the technical world of physics and the broader currents of human thought as powerfully as Bohr did. His discoveries, his ideas, and his vision of science as a global and moral enterprise made him not merely a pioneer of quantum theory, but a thinker whose impact resonates far beyond the laboratory. To understand Bohr's enduring legacy, one must see him not only as a physicist, but as a philosopher of science, an internationalist, and a symbol of responsibility in the atomic age. Bohr's name is forever linked with quantum mechanics, the theory that reshaped our understanding of the universe at its most fundamental level. His atomic model, though eventually superseded by more advanced formulations, was the key that unlocked the structure of matter and provided the foundation for modern chemistry, physics, and even biology. Every textbook that explains atomic orbitals or electron transitions owes something to Bohr's pioneering insights. In this way, his scientific contributions form part of the enduring infrastructure of modern knowledge. Yet Bohr's legacy in science is not limited to specific discoveries. It lies in the principles he introduced for thinking about the nature of reality, especially his principle of complementarity, which remains one of the most profound philosophical statements ever produced by a scientist. Complementarity was more than a technical interpretation of wave-particle duality. It was a lens for understanding complexity and paradox in nature. Bohr taught that reality could not always be captured by a single perspective, and that different, seemingly contradictory descriptions could both be necessary to capture the whole truth. This insight shaped physics in a practical way, guiding generations of researchers to think beyond classical categories, but it also spilled into philosophy and even into the arts. Writers, artists, and philosophers found inspiration in Bohr's principle, seeing in it a metaphor for human experience, for the coexistence of opposites, and for the need to embrace ambiguity in the search for truth. This cross-disciplinary influence ensures that Bohr's intellectual presence extends far beyond the scientific community. Equally important was Bohr's legacy as a teacher and builder of scientific communities. His Copenhagen Institute was not merely a workplace, but a crucible of ideas that trained and inspired some of the greatest physicists of the 20th century. The atmosphere of open dialogue and international collaboration he created became a model for scientific institutions around the world. Through the students he mentored, Heisenberg, Pauli, Gamow, and many others, his influence spread into every corner of modern physics. The collaborative culture that underpins science today, with its international conferences, shared laboratories, and global research networks, owes much to the spirit Bohr fostered in Copenhagen. But Bohr's legacy extends still further into the moral and political realms. As one of the few physicists deeply engaged with the ethical implications of nuclear research, Bohr set an example of responsibility that has become increasingly relevant in the modern age. He recognized earlier than most that the atomic discoveries of the 20th century carried with them both immense promise and catastrophic danger. His calls for openness, for international cooperation, and for the peaceful use of nuclear energy anticipated the global institutions and treaties that later sought to regulate atomic weapons. Though his warnings were not always heeded during his lifetime, the principles he championed remain central to debates over nuclear policy today. His vision continues to inspire those who seek to balance scientific progress with the survival of humanity. In society at large, Bohr's name has come to symbolize both the power and the responsibility of science. He stands as a reminder that knowledge cannot be separated from its consequences, and that the scientist must also be a citizen and a moral thinker. In an age where technological innovations, from nuclear energy to artificial intelligence, pose profound ethical challenges, Bohr's example of combining scientific brilliance with philosophical depth remains a guidepost. His life illustrates that true progress requires not only discovery but also reflection, not only power but also wisdom. Bohr's legacy also lives on in the institutions and structures he helped inspire. The International Atomic Energy Agency and CERN both carry forward his vision of international collaboration in science. Universities around the world that emphasize research communities over rigid hierarchies echo the model he pioneered in Copenhagen. Even the United Nations has, in its discussions on nuclear arms control, invoked the ideas Bohr first articulated about openness and cooperation as the only path to security in the nuclear age. These enduring influences remind us that Bohr's ideas were not confined to theoretical physics, but touched on the very organization of global society. Culturally, Bohr's legacy has acquired a symbolic dimension. He is often portrayed as the thoughtful sage of quantum mechanics, a man who embodied the intellectual struggle of a world moving from certainty to uncertainty, from classical order to quantum ambiguity. His debates with Einstein at the Solvay conferences have become legendary, dramatizing the great philosophical conflict between determinism and probability. In popular memory, Bohr represents the acceptance of mystery as a necessary part of understanding, and the humility required to acknowledge the limits of human knowledge. This image has inspired countless accounts in books, plays, and films, ensuring that his life continues to capture the imagination of the public as well as scholars. Perhaps most striking is how Bohr's legacy remains relevant in today's scientific frontiers. In fields like quantum computing, quantum cryptography, and nanotechnology, the principles of quantum mechanics, born out of the debates Bohr shaped, form the bedrock of innovation. The computers and technologies being developed today are direct descendants of the insights he helped crystallize nearly a century ago. In this sense, his legacy is not only historical, but also profoundly contemporary, alive in the devices and systems that are reshaping human life in the 21st century. Looking at Bohr's life and work, one sees a man who combined science, philosophy, education, and morality into a single coherent vision. He was not without flaws. His cautious style sometimes frustrated more daring colleagues, and his insistence on complementarity was not universally accepted. Yet these limitations only highlight the depth of his humanity. He was not a prophet detached from the world, but a thinker engaged with the uncertainties of his time, striving to balance discovery with responsibility and theory with life. This human dimension makes his legacy all the more powerful, for it shows that greatness in science does not come only from equations or experiments, but from the courage to ask the hardest questions about what knowledge means for humanity. In the end, the enduring legacy of Niels Bohr lies in the way he redefined the role of the scientist. He demonstrated that the scientist is not merely a solver of puzzles but a thinker, a teacher, a builder of communities, and a guardian of humanity's future. His ideas continue to shape physics, his philosophy continues to influence thought, and his moral example continues to challenge society. More than a century after his greatest contributions, Bohr remains a guiding light in the ongoing dialogue between science and humanity. His voice still whispers through the halls of physics, reminding us that in every discovery lies a responsibility, and in every paradox lies a deeper truth.